Hello students, in this video lecture we are going to discuss about the Morera's theorem, which is a converse of Cauchy's theorem. As Cauchy's theorem states that if a function is continuous and analytic, then integration of that functions around a closed contour is always 0. But Morera's theorem states that if a function is continuous in simply connected domain D, and if integration over a closed contour C of fz dz is 0 for every closed rectifiable curve C in D, then f is analytic in D. So for this, let us construct a domain D. Okay, so let alpha be any fixed point inside D and z be a variable point inside D. So let us join these 2 points alpha and z by two rectifiable curve. So let us denote them by C1 and C2 be any rectifiable curve in D joining alpha and z. So that the curve consisting of C1 and C2 to a closed rectifiable curve. So that by a given conditions, integration over C f of z dz is 0. Okay, so we are connecting alpha and z by two curve. Now integration along C1 plus integration along C2. So here we have to understand the orientation of curve. So it is a counterclockwise directions and this is clockwise direction. So sign will be positive if we are in anti-clockwise direction. If we are in clockwise direction, so sign is negative. Okay, so this is integration over C1 fz plus integration over minus of C2 fz dz is 0. So it is a consequences of a Cauchy's theorem, okay, for a multiply connected domain. If there is a closed regions, okay, inside a closed region, if there is another a circle, okay, so in that case what Cauchy's theorems states as, then integration over AC is equal to integrations over C1 plus integration over C2. So that what we are doing here is just putting these two in opposite directions. Okay, so whatever the path we follow to reach z or alpha from one point, that is independent of path. Okay, so what we can see here is integration over C1 fz plus integration minus C2 fz dz is 0. Okay, so integration over minus of C2 will be minus integration over C2 fz dz. So transposing that terms in the right hand side, what we get, integration over C1 is equal to integration over C2. So let us consider this. So equation number 1. So this shows that the integral of f is independent of path so long as the path lies entirely in D. Whatever the path we take inside D to reach one point from another point, that path lies in D. Okay, so let us define one function in D, phi of z, which is equal to integration from alpha to z fw dw. Fw is also a complex function. Okay, so just we are considering a phi z, and then again consider phi z plus h. Just we are adding h on z, then integrating from alpha to z plus h. Okay, so here we can assume that z in some point here we can consider z plus h. So alpha to z plus h we are integrating. Now this is equation number 3. Now subtracting equation number 1, that is phi of z from 2, what we get, 3, we get phi z plus h minus phi of z equal to integration from alpha to z plus h f of w dw minus alpha to z f of w dw. And what we get here is integration when we subtract alpha to z plus h, then alpha to z. Okay, then we get, when we subtract these portions, what we get, z to z plus h f of w dw. Okay, so first alpha comes, then z, then z plus h. When we remove z to alpha to z, what we get? Z to z plus h. Okay, so integral 4 uh, integral 4, this is integral 4. Integral 4 is also independent of path, and hence we need to take the same along straight line that is joining z and z plus h. So if we take z to z plus h here, so we consider that point can be a straight line joining 2 points. Okay, so now what we are doing here is phi z plus h minus phi of z divided by h. We are dividing both sides of this equation by h, and then again we are subtracting fz from both sides, subtracting f of z from both sides. Okay, so equality holds. Okay, it still holds if we subtract same numbers or same functions from both sides, and still equality holds. So we are using that only. Now here, why I am writing fz inside this integration sign is, since when we integrate f of z dw with respect to w from z to z plus h, we get h f of z. So we can substitute here, we can take fz inside this integrations. Okay, because when we integrate between these two limits with respect to w, we get h of fz. So 1 by h we can cancel out, so 1 by h integration from z to z plus h f of w minus f of z dw. So this is equation number 6. So now here we have to use the hypothesis. As for the statement, f is continuous at z for all epsilon greater than 0, then for L epsilon greater than 0, then for epsilon greater than 0 there exists a delta such that f of w minus f of z is less than epsilon whenever w minus z is less than delta. So this is epsilon delta definition of continuity. Now we can use these conditions. So we choose z plus h inside d, in d, such that mod of h is greater than 0 but less than delta. Then for every point w on the straight line joining z and z plus h, mod of f of w minus f of z is less than epsilon. Okay. Now hence from this is equation number 6, last equations which we have discussed. Now taking modulus on the both sides, what we get? Mod of phi of z plus h minus phi z divided by h minus f of z, which is equal to 1 by h integration from z to z plus h f of w minus f of z dw. So now this here we can use integral inequality. So in mod of integrations, f of z is always less or equal to integrations mod of f of z dz. So here we are using this. Now mod of 1 by z and integration mod of f of w minus f of z in mod of dw. So this is 1 by mod of z, keeping as it is. Now from the definitions of continuity, f of w minus f of z is strictly less than epsilon, so replacing this by epsilon. And dw is a arc. Okay, when we integrate from z to z plus h, so z plus h minus z, okay, that is the whole length is h only, difference between z and z plus h, so we can consider as mod of h. Now we can cancel out mod of h and mod of h, so only epsilon will remain, which is arbitrary, so small. So neglecting this, okay, and now taking the limiting value whenever h tends to 0. So in our left hand side we have phi z plus h minus phi of z divided by h. Now transposing this fz in the right hand side, we get this is now the derivative of phi at uh, this is a derivative of phi, so phi dash z equal to f of z. So now here phi dash z exists at each point of d, so this implies the derivative exists. Okay, so phi dash z is equal to f of z in t, so phi is analytic in d. At each point of d, derivative exists, so this implies that phi is analytic in d. Since f is derivative of analytic function, so it follows that f is itself analytic in t. As we know that derivative of a analytic function is again analytic function, so this proves the theorem, that is Morera's theorem. If a function if is continuous and integration over closed contour is 0, then that f is always analytic. So thank you.